In this video, I will talk about the theory when we have underdamping. And what I mean by underdamping is when the parameter beta is less than the parameter omega naught. Now, what are those? I want to remind you, let's go back to the theory. So I had defined beta to be B over 2m, where B is the coefficient in the resistive force, and omega naught squared was K over m. Now, in the case where beta is less than omega naught, then I can do the following. This is the general solution to the differential equation, and I see inside in the exponential I have the square root of beta squared minus omega squared, the same for both terms. Now I know that beta is less than omega naught in the case of underdamping, so what this means is that this is less than that. I will end up having a square root of a negative number, which will give me an imaginary number. Now, one thing I can do, though, I can take that imaginary unit I out of the square root even without doing any calculation. So what I can do is, okay, beta squared minus omega naught squared is essentially minus 1 times omega squared minus beta squared. So if I take out the minus 1 from here, it's going to give me minus 1 times omega squared minus beta squared. So I'm reversing the order here and take out the minus 1. But minus 1 is equal to I squared, the imaginary unit squared. Okay, that's by definition I squared is minus 1. And because I have the square root, I can take the I out. So this ends up being I times the square root of omega naught squared minus beta squared. And I can introduce one more variable, omega 1, to be this square root. Okay, so that's what I have in my solution, but I can write this as essentially I times omega 1, where omega 1 is equal to that. And by doing that, okay, at the end of the day, what am I doing when I do this? I just express this in a more simple way, but at the same time, I make it explicit that this is an imaginary number. And then this allows me, so if I say that this is the equation I start with, and I use this over here, then this will give me x as a function of time is, you know what, one thing I can do is take something out as a common factor. Since I have e to the minus beta in both of them, I can take it out, and then I will have c1 times e to the I omega 1, and this will be with the plus, that's the solution with the plus c2 times e to the minus I omega 1. I think I forgot the time. Yep, I forgot the time. So here and here, and because I have it there, that means I need the t here, and that also means I need to go back and fix okay, so here, oh, actually I did not forget it here. I did include the t. Alright, that's good. Alright, now what I'm gonna do is I want to show you what this represents, and this is a sum of the two exponentials. So whether I write it using a sum of two exponentials, or I can write it in the form of cosine now to get some more insight. minus delta. So what I've done, essentially, the two parameters of the differential equation here are C1 and C2. When I write it using the form of the cosine, the two parameters that I'm using are A and delta. Now, okay, I'm going to talk about the two factors that influence the solution. So in the case of underdamping, this is what I get. Now, this is familiar. This is a cosine. And when I multiply it with A simply controls the amplitude, how much it goes up and down. So let's see. So this is time. And let's do a cosine. It doesn't really matter whether we start with a phase of 0, with a delta of 0 or not. Okay. I will not set where the t equals 0. I'm not going to decide what is delta for me right now. But I do know that this is plus a, and it goes all the way to minus a, from minus a to plus a. Now, here's the thing. This is not the only part of my solution. I also have e to the minus vita t. And what this means is that the exponent of this exponential actually becomes more and more negative as time goes by. Okay, so as t increases, this becomes more and more negative. And I know that when I have e to a negative number, that the more negative the exponent is, the smaller the whole thing will be. Okay, let me show you what I mean with that. Essentially, the graph of e to the minus bt will look like this. Now, okay, something like that. Okay, it will decrease exponentially. Now, here's the thing. The solution in the case of underdamping is the product of this and that. Now, one thing let me make a slightly different cosine so that I can show you better with a smaller, with more repetition, so you can see what is the influence. Alright, so I'm gonna start here. I'm just gonna do some more ups and downs so I can show you a little bit better what is the result of the product. So when I multiply essentially this cosine graph with the graph of e to the minus vita t, what this will do, it will essentially decrease the amplitude of the oscillations as time goes by. So a, when t equals 0, imagine this, t equals 0, this gives me 1. The amplitude is just a. When t is 1, then this is going to be slightly less than a, somewhat less than a. When t becomes 2, the amplitude of the oscillations will be even smaller. When t is 3, the amplitude of the oscillations will be even smaller. So the amplitude is controlled by this exponential, and that is why the oscillations actually will not reach that low. They're gonna be I'm not sure. Let's see if I can show that. So if it starts from plus a, it will never make it to minus a. And now it's gonna be even less, and it will be even less here, and even less here, and even less here, and so on. Okay, So this part of the solution essentially modulates what will be. So this is gonna be an exponential decrease. Okay, if you want to superimpose the two, so this will be the e to the minus vita t part, and it will result in your motion at some point being very, very small. In the limit where time goes to infinity, of course, there will not be any motion, and that makes sense. We do have a resistive force in this case. It makes sense that the motion will eventually die out.